Okay, let's get started. Welcome to another Our Universe Revealed. Is the public lecture series from the physics department. This is our second to last event of the semester. We're back in 2 weeks' time. Hopefully the weather holds out for a little longer. We don't get more snow, but we'll see. But we're continuing today with nuclear physics in some respects, but applied techniques of nuclear physics, looking at how we can identify specific materials and things, and how we can do that perhaps in a historical context. It's my pleasure to welcome back Dr. Manukyan to Our Universe Revealed. He's been at the university since 2010, first in chemical engineering and then came over to physics in 2013. I was just asking him if that was a step up or not, and he declined to answer, so we'll leave that one there. But he has talked to us before about how we can use nuclear techniques to analyze historic artifacts. And today he's going to give us some context about that in the terms of counterfeiting and money. So let's give him a nice warm welcome. And over to you.
Thank you very much. Can you hear me back there? Okay. Thanks for invitation and for introduction. I'm really happy to come back here and present some of our new and old results. So on, okay, I'm confused. This one is not showing, Jonathan. So, okay, so this is about all science, a little bit broader terms. There are some nuclear techniques, but we use also lots of other techniques. So to answer the questions that matters for this type of research. So this is actually kind of hobby for us. We are not doing it in a more broader systematic. We're doing systematic basis, but this is limited to undergraduate education, and most of the data that I will show acquired by undergrads, and this is fun for them and fun for us too. And it's all about money. And first, I wanted to give a definition of money. If you search on Google, you will find lots of definition, but I would like this one to use, that money allows people to trade goods and services indirectly. So it's just tool to trade objects and services. So I also wanted to have some introduction about evolution of money. I'm sure you know this, but I just want to highlight. So at the beginning, there was no money. It was only barter system. People traded, products, and eventually a new form of money, which called commodity money, came at about 9000 BC. And those were primarily salt, grains, and livestock. And eventually, people started to use random objects at the beginning, crude metals, and then even shells and animal bones and the teeth and stuff like that. Around 1000 BC, then people started to use more standardized objects like this Chinese token, bronze token, and the coinage from Greece and also from India. And coinage was for a very, very long time primary media for exchanging for exchanging goods and for money. But at some point, the 7th century AD, Chinese and Mongolian people invented certificates. Imagine if you had lots of coins and you want to go some other places, you don't want to take all of the coins with you. You could go to a specific office, specific place, and get this certificate, give your coins, and then after traveling, you can go present this note and then get your coins back. So this was pretty efficient and eventually, but it took about 10th century, then Europeans adopted this. In late 17th century, European private banks started to issuing banknotes. And soon after, the England started to issue first paper money, which was 1694. And a year after that, American colonies, Massachusetts, for example, issued first American colonial currency. It's specifically good for this research because we are showing some of this data. And paper money was for a very long time one sole source of the or main source of like trade, not source, means of trade. Of course, paper money was always backed until maybe 70 years ago with the gold standards or other metal standards. But eventually, in mid 20th century, US and Britain, they just abolished that policy. They didn't use metallic standards, and it becomes only paper. But eventually, paper started replaced by plastic money or borrowed money. And eventually now we are seeing another revolution, that we are going to a new technology, which is cryptocurrency. This is new. We are not going to talk about new today. We are going to talk about the old things. And I would like to just highlight broadly, we can categorize counterfeiting in two ways. One is just modification of existing money. The other is the faking, creating completely new money, which is not a legitimate one. And fake money is usually produced by individuals, criminals, or produced also by officials. Some means, some official organization, or along the history produced, different types of non-legitimate money. One example, which is not exactly true that I said, but over about 250 years, British Empire, Roman Empire produced debased Roman coins. We'll talk about that a little bit later. But first effort to use that technique as a warfare was introduced by British during the American Revolutionary War. So British military injected in American colonies lots of fake money to counterfeit, to decrease the value of money and eventually win the war. But that wasn't successful. Eventually, they used also faked French money during the French Revolution, and later on during Napoleonic Wars. So that was also happening. French did that for Austrian and Russian money. And eventually Nazis, they did also for British money. So this became a kind of very common tactics to win the wars. So for today's topics, we are going to tackle some of the objects that we are fortunate to have in this campus. So we have a library, and in library we have these rare books and special collections. And we have thousands of coins and paper currency, mostly from colonial Spanish and American times, also colonial paper money. So we'll talk about this, and then we are using multiple techniques to analyze those objects. Some of them are shown here as images. So this is a particle accelerator operating at a nuclear science lab at physics department. We have some other smaller instrumentations like handheld XRF, or we have microscopes at the campus. Actually, recently Notre Dame acquired really outstanding microscopes. So I will show in the last images one of these results gathered from the transmission electron microscopes. A full list is here. I'll try to explain some of these techniques along the way of showing the results. So first, I would show some of the results about Roman coins. Just for introduction, for Roman monetary system. So before imperial times during the Republic, so mostly the highest denomination was denarius. It's a silver coin. They had some other silver coins and a bunch of other copper coins. But after establishing empire, after Augustus, so they started to mint also gold coins, aurus, which is aurus is a gold in Latin. So, but for a long time, denarius stayed as one of the main types of money, because it was not very expensive. It was also not very cheap, so it stayed a very nice middle ground, and for everyday transactions even more. So, but if you look at the history, there is a very interesting insight. So if you look at the beginning during the Roman Republic, the denarius was 4.55 grams, and it contained about 98% of silver. But after Roman Empire established, so about 50 BC, during Nero's time, so the amount of silver becomes smaller. So it's 93.5, and over the time, these emperors decreased even further to 50%. And eventually at 259 AD, the percentage of silver became only 5. So at that time, public realized that there is something going on. Before that, about 250 years, public never realized how that could happen, that you decrease the amount of silver to 5%, but the coins look still nice and fine, shiny and fine. So that was one of the questions we tried to answer, how they managed to do it. So for that, we had a private collection by Professor Vischer sitting here. So he graciously provided these 20 coins, ranging from 136 BC to 240 AD. And the collection was exactly meant he bought this because of these purposes. So we have every type of major emperors here. You could see names. My favorite one is Marcus Aurelius, because he was philosopher and very wise man compared to some other emperors. We have also republic coins. So the goal was to probe them, all of these coins, and try to understand how they made these things work, that they debased with the copper, but public never noticed that. So the first technique that we used, it's called X-ray fluorescence. So this is a very easy technique, we have two devices, and the basics is that you shine your material with X-rays, and inside your material's atoms, you generate, you ionize some of the atoms, some of the electrons are jumping out from atoms, and then inside the atoms, we create specific electronic transitions from upper shells to lower ones. And during that electronic transitions, atom emit secondary X-rays. And you could see here a diagram which shows the ionization of arsenic atom. So electron from K shell moves out, and then just after that, 2 electrons from this shell and this shell jumping to here, and then you also have emittance of characteristic X-rays. And these processes manifest themselves as these 2 lines, which are very characteristic for that arsenic metal element. And this could be used to identify arsenic. If you have multiple elements, then you have multiple lines, and then you can do even quantification and find out how much of these elements you have in the sample. So we have 2 instruments. One is large, pretty unique and nice instrument. You can do lots of this, but this is pretty large instrument. For some objects, for example, we are using these techniques, artifacts gathered from archaeological sites or from museums. So this instrument is hard to move there. Therefore, we have this smaller instrument, which is handheld. You can take and go to museum. It's just, you can put in your hand and then use it. Both these techniques have the same principle. We have X-ray source inside. You shine with X-rays the object, and then characteristic X-rays generated from object collected by detector, and then analyzed by spectrometer, and then eventually you get spectra on a computer, and then you can do lots of quantification. So the first complicated instrument also has these features. You can have a very small beam of X-rays, and then you can scan the surface of the beam and generates hundreds of thousands of spectra from each data point. And then after processing this data, so you can generate this color-coded map for entire object. So here, for example, in this coin, we can see that this purplish area contains a lot more copper, and the more this blue area is more silver. There are some other elements also which I haven't noted here. So this allows you image the surface composition of coins, and not only coins, other objects too. So here you could see some of the results from coins minted at, for example, 136 BC. It really contains mostly silver and not much copper. And over the time, if we go forward, so 30 AD, 65 AD, this is Emperor Nero, and then Aurelius, you could see that silver concentration slightly decreasing, and then you can notice that this purple intensity of copper X-rays becoming more pronounced, and then you can see this nice color of copper here. But if you move even further, now copper become a dominant, so you have a lot more copper than silver. So this is also proving that they incorporated copper into the coins. But then we use the nuclear technique. Actually, this is difficult to say sometimes nuclear. It's an ion beam analysis technique. But the idea is that we have accelerator, we have ion source, so we generate ions, in this case protons, and then we shine our object with the protons, accelerated protons. And here is an image from Florence. Every major museum in the world, they have these types of accelerator. So then protons shining on the objects, and then you exactly having the same processes in the atom as XRF. So you're generating secondary X-rays, and then you analyzing this with this detector, that X-rays, and that allows you to determine atomic composition, or even this method provides higher sensitivity to trace elements. So then we took advantage of these two techniques. So we combine them together. We use X-ray fluorescence. We use PIXE with different proton energies. And this allowed us to have some, we call it depth profiling. So because X-rays penetrate deeper layers, so we can probe the composition at slightly deeper layers from the surface. And tuning the energy of proton beams, we can probe a little bit shallow layers of the object. And by doing so, we can have an idea if the surface has different composition a little bit farther away, what's the composition is. And the results are plotted here. You could see this x-axis is time, is year, and the BC before Christ, this is AD, and the y-axis is copper amount inside the coins, At the beginning, we truly have a very little amount of copper or even none of it, but starting 50, 60 AD, so you could see the copper concentration increasing every time, in every coin, and you can see that in the deeper layers, in the core of the coin, we have much more copper, about 60% in this case. But on the surface, we have much less copper. So it means that they have some sort of technique. They made this coin, which is copper rich inside and silver rich outside. And how to do this? So we turn now to microscopy techniques, so to understand. So electron microscope is another type of accelerator, except that you are generating electrons, you're shining electrons with these electromagnetic lenses on the object, and then you generate here secondary electrons, which you can use for imaging purposes. And also there is a possibility to do element analysis using this technique, energy dispersive X-ray spectroscopy. In addition to this, we also have ability, which is nice for these objects, to do micro-destructive analysis. So I'm going to play a video here. So you can see this is an object, it's not coin. And what we are doing here is you can zoom in, focus, and this is 10 micrometer, is about 10 times thinner than human hair. And we can mill this area with ion beam. So entire sample still stands. We are not destroying it, but we can make a small cross section here for analyzing imaging, you would not be able to see this damage by eye. You just need to go the microscope to see again. So in some cases, these types of analysis is important because people, this is the only way to see on these objects. So in this case, we generate this cross section and we started to, let me go, sorry. Okay. And then we looked at sidewall that we created. And what we see for this specific coin, this is Caracalla 213 AD. And we see a nice layer on top of the surface. Surface is roughly here. So which has a metallic shiny color. And underneath this layer, we see two different faces. Shiny faces, which is much like this one, and gray face. And then if you look on the mapping, so we can see that this shiny part is silver, and these core faces are mostly copper. So again, they had a layer on coin, which is silver rich, but inside it's a lot more copper. So how they do this? So most likely they melted these two metals together, they casted alloy, and then after that they hammered to get a thin sheet of the blank coins, and then they inserted that blanks in a flame. And because copper is much more susceptible to oxidation, then very surface layers, copper grains were oxidized. And after that, they dipped this coin in an acidic solution, vinegar or lemon juice, and oxidized copper leached away, but silver was not oxidized. So then after that, you form these pores, which were before copper. Now it's just voids, all these black areas. And you're just artificially depleting on the surface. And after polishing or burnishing, you have a shiny surface, but copper color inside the coin. So this was one technique. And actually this technique still is in use for production some of the coins. But what we discovered, which was new, that they also had another technique. For example, in this case, when we have this coin minted by Emperor GETA, so you could see here, this area is copper rich. And then when we make this imaging, you can confirm that we have lots of these darker gray areas, which are copper, and those are silver, more shinier area, no, more lighter areas. But if you look on this region, so where we have mostly silver, we have this interesting microstructure, which very small grains, but they are pure silver. And again, so we could still use this technique to produce. Let's see if. Yeah. So what we saw before, that we made a trench, and now what we are going to do, we are going to cut that small area and transfer that sample, a small, much smaller sample, to another electron microscope. So with ion beam, we cut that area. This entire thing is done under the microscope for 3 hours, for about 3 hours, but this is just accelerated video. So you could see there is this probe, which you can weld the sample of interest. So then it's welded here, and then we lift it off and then transfer this piece of sample to another holder. The original object is free. It could go back to museum or wherever it came from. Then we can keep this sample. We can use the ion beam to polish that to about 100 nanometer thick, which is 100 times thinner than human hair, and then transfer it to electron microscope, another electron microscope. In this case, electrons passing through the sample. Sample is pretty thin, and then you can get lots of information out of this analysis. So, and what we get from here, that for this specific coin from this area, we get this interesting microstructure. And then looking at these areas, we found lots of mercury. So, and the other technique, which is inside the microscope, allowed us to determine this. We have a silver mercury alloy, which is amalgam, silver amalgam. So, and what we think that how they managed to do it. So now I'm going to show a video, which is not silver, but gold. So, and this is a gold foil. And if you pipette small amount of mercury on gold, what's going to happen that gold will be dissolved in the mercury. So you will see over the time, so this gold slowly dissolves. Exactly same happens if you use silver. I just don't have the video for that. It's a little bit accelerated video, so it's not real time, but eventually, so what's going to happen that the solid gold dissolves into liquid mercury, and then you are getting the pasty type alloy. It's a liquid alloy, and this still can dissolve some of the gold. The idea is that most likely they created this copper silver blank coin, and then they use silver amalgam paste. They apply it to the surface of the coin, and after that it generated it was easy to apply, and then they heat it up, and you could imagine that mercury can go away. It's low melting point material and evaporates at lower temperatures. Of course, this was a very nasty technique because mercury is poisonous. And then eventually they created a very thin layer, about 2 micrometer layer of pure silver on the surface. Of course, the layer was not having high quality, and over the time it worn out, and it's most of it not there anymore. So this was one thing that we discovered. We published a paper, scientific paper about this in a scientific journal. But then we also look at the much younger coins minted from Latin America and South America and Mexico. So those coins were from Potosi and Mexico City. Actually, they were not actual coins. Those were minted just after mining silver. They had this shape. They shipped to Spain for further melting down and then for producing real reals with 92.5% silver. And there was also a historic question that during 1652, first mint was opened in North America in Boston, because American colonies always had shortage of metal coinage. So this was the first attempt to have some means for trade. And there is an idea that the mint master used one of these silver sources to produce his new coins. And most likely they melted one of these types of coins, added some more metals, less precious metal, and then to make it financially profitable in order to operate that mint. And when we analyze this, about 100 silver reals and then Boston coins, so we find out very interesting cases. At this region, we see some of the coins from Potosi were containing a lot less silver and more copper. And it turns out that this was historic event. At 1648, there was a huge scandal. Mint masters at Potosi, they deliberately added copper. They cheated on king, and they shipped that coins, crude metal, to Spain. When that uncovered, it created huge financial problem at the time. And then we can actually see that here on these specific coins. And which is really timing is really happening at that time period. But another interesting thing that we figured out that Boston coins contain a lot more iron and copper. So what essentially Mint Master did, he melted one of these Latin American coins, added some copper or iron, to reduce amount of silver, and then that's made a financial profitable. So another interesting object here that when we look at the trace composition of gold, so we can see that POTOSI coins have literally not much gold, those square points, but Mexican coins had a lot more gold. So it's about 0.3% gold inside the Mexico City coins. But we do see also some elevated level of gold in American coins. This allows us to suggest that probably Mexican coins were the source for minting American coins. So last piece is about paper money. And you all know about this guy. He is Benjamin Franklin. He is one of the founding fathers of United States. He is really embodiment of American dream. Becoming from very humble beginning, he became a very rich person and eventually became one of the founders of America. So one of the first, his business was printing, and he was printing colonial paper money. He was advocating a lot about paper money because American colonies, as I mentioned, they had any coinage. So the paper was only source for trading. And Franklin established a kind of empire for printers. He just established different printing shops at different colonies and team up with these people. They printed from the colonial paper for different colonies, and eventually they also printed money for Continental Congress. During the Revolutionary War, Congress authorized to print money for covering the war expenses. And David Hall, who was Franklin's associate, his former partner, get this commission. And Franklin was also in charge of designing this paper money. And all over the printing time, he was also creating new types of paper to print this type of objects. So when he started to print paper money in 1732, first emission of Pennsylvania currency, the first emission was faked a lot. And then he started to think about the ways that he can combat counterfeiting. One solution was to print these leaf structures. They call it nature printing. They use natural leaves to obtain this interesting vein structure. The idea was that it becomes difficult to fake it, copy it, but that wasn't enough. And then he started to deliberately misspell some of the words, which prevented the modification of some bills. But then he developed many other techniques and tools. But during the Revolutionary War, when they printed continental money, so British dumped lots of fake currency in American colony. And we can see that this is the legitimate paper money printed by Hall and Sellers. And what we see here, this black pigment, mostly containing carbon, graphitic carbon determined by Raman spectroscopy. But counterfeit money contains calcium and phosphorus, and Raman spectroscopy shows that it's a phosphate ion, which is confirming that this pigment, black pigment, was derived from bones. They pyrolyzed bones, and because bones has calcium and phosphorus, even though it's black ink, it contains lots of carbon. It's still black. But you could see calcium and phosphorus on X-ray fluorescence spectra. So this was one way that we can determine the counterfeit money. But another very interesting thing was that when we scan this money, this is legitimate one. You can see inside the bills, inside the paper, some of these inclusions which contain iron, some aluminum, silicon, potassium, and titanium. So they introduced some inorganic pieces inside the paper. And then we analyzed about hundreds of these paper money. And we do see that early on, there was no inclusions. The early papers, there was no inorganic inclusion. But over the time, they incorporated these particles, which you could see with these colors. And those are from different colonies and from different dates. And particle size is increasing, and they eventually becoming really large, up to 5 millimeter large particles. And this is the largest one that we encounter. It's one of the largest one. So it's about 2 millimeters. So they are shiny crystals. If you tilt the beam, they reflect light. So, and another example here that in legitimate money, you can see lots of these inclusions, but in counterfeit one, you don't see those. You also see potassium as part of signatures, but the potassium coming from these inorganic inclusions, you cannot see them. And this was one way, I think, that they introduced these inclusions initially to give paper some mechanical robustness, but then eventually they probably, this is just assumption, they figured out that these shining crystals can serve also means for combating against counterfeiting. So then we use this novel electron microscopy that I mentioned. So we took a sample from that crystals, and then we ran this imaging, and those are atomic layers. So, and then if you look here, after this is real image, this is some sort of processing image. So we can identify single atoms. For example, those dots are potassium atoms. And this layer is mostly silicon and oxygen layer. And here the same. And in this intermediate layer, we have mostly aluminum. So then we analyzed these structures, and then we figured out that this is mica crystal. So mica is very interesting mineral because of this internal structure, this layer structure. It could be exfoliated, and eventually it could, they use it to mix with the paper during the paper making process. So ideal composition of mica is this, but in reality, you always have some substitutions of some metals, and then our measured composition is this. So this was another way that Franklin and his associates used to make money, and then these features were used to kind of secure the money. So it's interesting that over 100 years during the colonial time, pre-federal time, so local printers develop really nice designs. They come up with ingenious solutions to combat all of this underworld counterfeiting, which was individual process. So, but eventually when British military machine came, and they dumped millions of pounds of this fake stuff, the value of this money became zero. Even historic accounts tell that people just took it, lots of them, and then stick to their walls as a wallpaper. There was no value at all. So that was irony. About 100 years of development, it becomes worthless. And but it helped later on during the United States to create a new type of monetary system. All of these features that I described, these mica crystals and also colored fibers, they are right now used in dollar production. Those were invented during this colonial times. So the conclusion is that using these sophisticated techniques, spectroscopy, ion beam analysis methods, vibrational spectroscopy, electron microscopy, we can efficiently analyze the composition of these materials, historic objects. We can also understand the most of the production methods. They that time people developed to make these objects. And most importantly, knowing this composition and information, we are able to help people to preserve these objects for future generations. So in the end, I would like to thank our our team. So most of this work is done by undergraduate students. So during the semesters or during the summer projects, so you could see from physics, from chemical engineering. We actually last summer, we had a visitor from New York University, from our conservationist department. She came here to do this research. Our another student now, she's at New York University as a master's student. And some of our undergraduate students helped on this process, the analysis. And I would like to thank my colleagues from physics department, and also Lou Jordan from library, who provided all of these materials for analysis. Primarily work is done at Nuclear Institute of Structural and Nuclear Astrophysics, which is nuclear science lab at physics department. And we also used resources of these two user facilities at Notre Dame. The funding mainly come from Notre Dame Office of Research. This was a part of a grant that we obtained a few years back to do this research. And in the end, I'll just advertise that we publish a book which is all about these things and much more. So you can buy, or if you would like to read, we can lend one. And we have all of this data there, and we have much more information about this type of work. And finally, I would like to thank all of you for your time this late hour, for coming by and wanting to more listen and then know more about this work. Thank you.